Hello, my name is James Hermus. I'm a graduate student in mechanical engineering at MIT. Today I'd like to share some results from human crank turning experiments. We found that features from free motion persist during constrained actions. The motivation for our work is that humans drastically outperform robots when it comes to complex physical interaction. One example of this is Alex, a mechanical engineering student winning a yo-yo national championship. A second is Adam Woodridge using a flexible, highly nonlinear material, a bullwhip, to knock the cap off the bottle from several feet away. Despite slow neural communication and low muscle bandwidth, humans frequently outperform robots when it comes to physical interaction. Interestingly, the majority of motor neuroscience has focused on relatively simple, unconstrained motion tasks. To bridge this gap, in this work, we studied crank turning, a physical interaction task which involves a circular constraint. By studying this simpler task, we hope to discover fundamental insight about physical interaction, which we later can apply to understand the more complex tasks, such as the yo-yoing or the whip cracking. Background for this work is that for more than 30 years, a relationship between curvature and speed has been reported in human handwriting, reaching, eye movements, and even walking trajectories. For this reason, it has been attributed to neural control. This finding was first reported by Abend in an experiment where subjects were instructed to move in a semicircle. They observed that subjects were unable to move in a perfect circle, and they observed errors in curvature. As a result, they found that the curvature peaks always corresponded to velocity valleys. As we previously discussed, if the humans were instructed to move in a circle, we know that they wouldn't be able to do it perfectly, and that errors would result where the curvature peaks correspond to velocity valleys. Now, one reason why a crank turning experiment is so interesting is that a crank confines the hand to move with constant curvature. Thus, we'd expect the velocity to be constant because the curvature is constant. Interestingly, in our experiments, we observed consistent velocity and force fluctuations with respect to position. We wondered, could humans be using the same approach, however, the interactive dynamics of the hand and crank mask the behavior? Thus, we hypothesized the underlying neural commands will exhibit the same patterns evident in unconstrained motions, specifically the speed-curvature relationship. In fact, this is what we observed. Now, the important question here is, how were the underlying neural commands estimated? The underlying neural commands were estimated by subtracting the mechanical impedance of the limb. Thus, this result suggests that humans leverage mechanical impedance to accomplish physical interaction tasks. I'd like to acknowledge our collaborators and sponsors, and thank you for your time.